So good evening, everyone. Just confirming, can I start now or should I wait for some more time?
Yes, I think we can start now.
Okay, yes. So, welcome everyone. So in this session, like this is a continuation of the previous session that we had regarding statistical analysis of network data with R. I am Spandan, and today we will continue our discussion. Specifically, we will discuss about the chapter 4 of that book, and not the entirety of it because this is quite a long chapter, but I will try to cover the introduction of descriptive analysis. Like when we study statistics, there there is some so there is like the descriptive statistics aspect, and we learn about basic things like some measures of centrality, measures of dispersion, and things like that, right? So here, in case of graph data or graphical data analysis, what we do, we learn about different descriptive measures that we can define for a random graph or a network data. So we start with like this, just the introduction. So many real questions can be restated on a network. Like we can have groups, we can have paths between different vertices. We can define something called as importance of a vertex, or we can also do something which is very popular and called as community detection, like detecting groups or clusters in a huge network data. So we will discuss mainly some simple summary measures like what is cohesion, what is centrality, what is partitioning, and things like that. So the very basic things that we can start studying in any like graph or network data is like the vertices and edges, right? So we can also start with specifically the degree of any vertex. So the degree is like how many links that the vertex has, or how many other vertices it is connected with. And for weighted graphs, this degree will convert into strength. That is the total weight of all the links that are going out or that are connected with a particular vertex. So, for example, in the Karate Club data, if you recall in the last session, in fact, I also forgot like exactly what the data was. The data basically is of an university karate club where many karate students are there of different qualifications, and I think some two, three instructors or masters like who are black belt are there who are leading the club, and some ironical like things happened. So as a result, the club split into two groups, and two groups means there were two instructors who were instructing two other groups, and those two groups had some common people like those who are like passing news from one group to another. Those things were there, but here what we are essentially seeing is the degree. So if you just think about the uh, like, okay, maybe I can open the first session slide as well. Is that also visible? Can anyone confirm if the other slide is visible?
Yes, it's visible.
Visible. Okay. So yeah, this is the Karate Club data. This was how the graph looked like. And here, basically, this John and Mr. Hai, they are like leaders, and they had their groups which are colored by with blue and red, and the edges that are connecting um, vertices of both groups are colored as yellow, whereas edges connecting vertices in the same group or the blue group are colored with blue, and same as the red one. Those are actually weighted edges. Okay, so that I think that shows how much this okay, so shape is practice. I think like the level of connectivity with any two people, like people they are very close or they're occasionally they interact. So things like that. So that is the basis of it. And basically for yes, I think Pratik has raised hand.
Yeah,
Mm.
so Professor, here I have a question just to
Mm.
understand intuitively that here what would we mean by the strength of the linkage? So, for example, if a linkage is more strong over here in the karate data set,
Mm-hmm. Mm-hmm.
what does how do you assess the strength of their relationship between the two people essentially?
Uh, yes, so just let me see. Strength, if I recall correctly, just a minute, I had it somewhere. So this data set is actually classical. It is referred in many textbooks of network data analysis. In fact, I have the book. So just a minute. I'm just referring to it. And strength of a vertex. Okay, basically it says that the sum of each weights attached to that person is the strength. And what is the weight? So the weight are based on number of meetings. Yeah. So number of meetings or events that has taken place, like some matches that those two players have played, right? So this
Okay,
is
so
this
the
is what the
number
yeah.
of quote unquote meetings between the two persons,
Huh.
the more strong is the linkage in this
Yes.
context.
Yes.
Okay.
Exactly. Thanks for asking the question. Yeah. I was also not I forgot what it was really. So so that is the strength. And having said that, if we plot the distribution of the degree, these are like simple histograms, or you can think of them as bar plots. When we are plotting the degrees, they are integers, so that can be thought of as bar plot. And the strength will be like some numerical value, because number of interaction means that is also some sort of integer. So this gives us the degree and strength distribution. And this is like, okay, so what does it tell? So basically it tells that the highest frequencies are for like lower degrees. So most of the nodes or vertices, they have relatively low degrees, right? And compared to that, if you see the strength is kind of more connected rather than the degree, because of discreteness that is inherent, that inherently comes with degree. And however, strength will be more homogenized, right? So that is one reason. But this is what it tells, that most of the degrees are in the lower side. So it is a skewed distribution, right? Even though there are a few, precisely two people who have very high degrees, right? I don't know whether the cursor is visible. I am hovering around these 2 points. So these two, I think, would correspond to the leaders, John and Mr. High or whatever. Okay. There is another data, and for this data, this is a little bit different data. Firstly, it is huge in size, and this is in the iGraph data package in R. So it is consisting of physical interactions in Saccharomyces cerevisiae. We all studied this name in our like school level. That is Baker's yeast, right? So this data consists of proteins in the yeast organism. These are the vertices. So what is an age? An age is experimentally observed physical interaction. So proteins inside this yeast bacteria, they interact with each other. And those protein interactions is basically the root of all biological activities that is taking place inside the organism. So what it signifies is that how different proteins interact. And if some proteins are interacting with most other proteins, that means they are of more importance perhaps. So here, in fact, this kind of a thing is seen, that This is firstly an undirected data set because we don't know the exact direction of interaction. We just know that these two interact with each other. And what is seen is that this shows a scale-free pattern. So what is a scale-free pattern that I will come into later? And the main observation is that many proteins interact with few other proteins, but a few hub proteins. What are hub? That also will come up. So just keep these terms in mind. So these hub proteins interact with many. Okay, so this is the thing. And the last point is that these are used to study cell function, and the graph is basically how would it be used? Like how the cells function, how the proteins interact, and what are the importance of each and every protein. So there's a huge data. So for this, just like if you have a large data set, just seeing each and every value will be very tedious and less fruitful compared to giving some summary measure. Similar is the thing here. We make the degree plots. So the degree histogram tells us a story that most of the degrees are very close to 0 and 10. So mostly they are low degree vertices, many low degree vertices. However, there are a few high degree hubs, like here, somewhere here. And what is this log degree distribution? That is like you have plotted log intensity versus log degree. So what is exactly intensity? It is, I think, intensity is that so like the frequency basically, frequency, nothing else. Like how many times this particular degree has come up. So you're plotting that. So what is happening over there? This has a underlying theory that will come up in the later chapters where we will use models, where you will use some formal models to explain the behavior of any random graphs or any type of networks. So there is something called as degree distribution. So we can fit a model to this degree distribution. So like when we have a count data, number of errors or misprints in any book or in each of the pages, we often use Poisson, right? Poisson distribution to model the number of misprints. That is a count that can start with 0. And it would essentially take low values, so it would be skewed. However, in theory, it can be infinity also, right? Or it can be very large. So here, scale free actually means that the degree distribution is not degenerate, rather it follows a kind of power law. So power law, those things will come up later. So basically, if you just take the log of those frequencies, that will be linear in degree, right? If you see here, we can see a linear pattern of the log intensity and log degree. So that means ki the expected frequency and the log of that is linear in degree k. So if you take out the log, then the expected frequency is something like 1 over k power alpha, where k is the degree. So that is a power law degree distribution. And that can be seen here in this data. So these are some of the conclusions, like most proteins have very low degree similar to magnitude to low degree nodes in smaller networks. There is also a non-trivial set of hub proteins which has much higher degree, like some are here with very low frequency. Now from the log degree plot, we can see that the log plot shows approximately linear decay in log frequency versus log degree. This suggests a scale-free pattern, though careful statistical fitting is needed for the degree exponent. Basically, once we see that there is a linear pattern, we can fit a distribution just like we do fitting of distributions in ordinary cases. So there are tests and all that we will study in the upcoming chapters. This is building intuition, right? So neighbor degree relationship is like high degree proteins tend to connect with other high degree proteins, and low degree proteins connect to both low degree and high degree proteins, showing mixed connectivity. Basically, from this plot, from this area, they are concluding that. So whatever we can conclude out of the plots. Okay. So this is like just the start. We have made a histogram plot of the degree distribution or a log-log plot of degree versus intensity. Next, we move on to the next concepts of vertex centrality. So what is centrality? Centrality quantifies the importance of or influence of vertices in a network. Like we all know that in a society also, there are many people. If you think them as vertices, there are a few important people in every society, in every social structure who are managing lots of things, right? So similar kind of uh, analysis is being done. So we want to detect who are those important or influential vertices. So what are the different definitions that reflect aspects of importance like degree? So it means that they are well connected, closeness, betweenness, and basically eigenvectors. These three we will now learn. This also tells us something. So let's go into them. So the closeness centrality, what is that? Closeness centrality, so it is for any vertex, right? So for any vertex, V, you calculate the distance of every other point that is inside the vertex set. You calculate the distance, you take their summation. That means if the distance are all quite small, so most of the points are close to the vertex V, then the reciprocal will be large, right? If the distances are large, then the reciprocal will be small. If it is small, if this closeness value is small, that means this is large. So this point V is in the outskirts of the network. It has very few connections. Most of the points are quite distinct or distant in a way. This is just a normalized version where we are putting n-1 so that things get balanced. That is the same thing, just a proportionality constant. So a vertex with small average distance to all others will have a high closeness. And this captures how quickly a vertex can reach to the nest of the network. So I hope this concept is clear. Now, this is just a plot for, I think this is the Karate Club data, if I recall correctly. So each vertex has a size. So vertex size is proportional to closeness or closeness centrality. So you can see these vertices are slightly bigger than the other ones, but the differences are not that like striking or prominent, which is one of the issues of closeness centrality. For that purpose, different other ideas are proposed, like betweenness centrality. So the next thing we will see is betweenness centrality. What does it do? It also calculates a ratio. It basically sees the number of shortest paths from S to T, and it sees the number of those paths passing through V. So it will consider all S not equal to T not equal to V. It will take the summation. V is fixed. It will take sum over all S not equal to T, removing the vertex V. And it is seeing for any pair S comma T, how many shortest paths are there. And how many of those shortest paths are passing through V. That means V is intervening in any of the shortest path. If it is always included, so if like sigma S comma T slash V is same as sigma S comma T or close to that, means most of those short paths are passing through V. Now that means the ratio is also quite large, and this means that this high betweenness means that V is a broker or a bridge in the network. So basically anything that you want to do, you have to pass through V, or any interactions between any nodes mostly passes through V. Yes, Pratik.
Yeah. So here,
Hmm.
Professor, here I would want to slowly build intuition for myself.
Hmm.
First of all, the definition of sigma s comma t, the very first line, it says number of shortest paths. So,
Hmm.
first of all, how can there be more than one shortest path? That is something that we may
Oh,
have
okay.
discussed.
So non-unique shortest path is like those paths which has lowest number of edges, right? Which we have discussed, I think, in the last session. Now there can be say two vertices, so like two paths of same length or three paths of same length. The shortest path length is 3, and there are multiple paths with length 3, say. So then that will be 3. Sigma s comma t will be 3. And two of those pass through V. So sigma s comma t slash V will be 2.
Okay. Okay,
Okay?
now I
Yeah.
now it makes intuitive sense, and I'm just saying a statement. I want you to correct me if I'm wrong.
Hmm.
So the fact that this betweenness is high means that naturally the numerator in this
Hmm.
ratio, the sum of ratios, the numerator must be high,
Yeah.
which means the shortest path include that point V.
Yes.
So V, that is why V is like that, socially very present person who
Ah.
everybody
Yeah.
interacts with. So
Yes.
that's why it is kind of a broker. Everybody
Bro.
has to go through it.
Hmm. Hmm. And now there are some issues with this, as you raised the point. Like we are taking the sum outside, and that the issue of normalizing or comparison would be there to some extent. But for a fixed graph, all the values are comparable because we are taking sums of the same magnitude, right? But between two graphs, these values are not that comparable. I mean that is what I am just thinking now. Maybe I could be wrong, but we are taking ratios. Each ratio will be between 0 and 1, but we are taking the summation of those values. Now that upper bound will depend on how many edges are there. So we should normalize this with something. Then that will be best. Like normalizing with all possible such pairs. Like something like, I think, n minus 1 choose 2. It should be n minus 1 choose 2. Because we are deleting v and we are taking s comma t pairs. So either n minus 1 into n minus 2 or n minus 1 choose 2. So yeah. Yes, sir. Like, does that answer, Pratik? Huh?
Yeah,
Huh.
thanks.
Huh. Okay. So similarly, we can see the plot of this. And here the differences are more prominent for some reason. And but again, this has one flaw. From a philosophical point of view, this also has a flaw. Not just a flaw, but you can think something better actually. What is that? So we are taking into consideration each and every edge, and sorry, each and every vertex. Like we are saying ki if we are taking any pair and the V is lying on that path, that's a good thing. That is what we are saying. But again, some vertices in this entire graph are important and some are not that important. So like it is like people who are connected with the most influential persons. Say someone is connected with 10 influential person and another person is connected with 20 people who are very less influential. So from a graphical or this kind of a ideology, the first person would be more like central, right? So kind of you can think of that person like someone in the Rajya Sabha or in those government positions. There's many big connections compared to someone who is in a distant village who has many connections with many people but not that influence. I'm not saying someone is less important or more important, just for the sake of explanation. So there to deal with that, more technical things are required. And there the idea of eigen centrality comes. Now, eigenvector centrality is something difficult, something quite difficult to explain. So even I don't exactly understand it as of now. I will need to study it more. I will just try to say what it does. So it considers the for the graph v comma I, it considers the adjacency matrix, which is like 0, 1 power n cross n means the set of all matrices whose entries are either 0 or 1. So AUV is, as you all know, AUV is 1 if U comma V belongs to the H set, which is an unordered pair. Because I am considering as of now only undirected graphs. These are symmetric matrix. So A is equal to A transpose and A is non-negative definite. A is non-negative definite. Now, centrality vector is an eigenvector such that C is equal to alpha A C. Basically, that is like AC equal to lambda C, the definition of eigenvectors. Now, here lambda is alpha inverse, and somehow we calculate the importance of the vertex V as the alpha times the summation of all neighbors of V which are there. So basically, we get the importance out of this eigenvector C. Now, this eigenvector also has some very special properties. I'm just mentioning the algorithm, but not going quite deep into the theory. That itself deserves a single lecture. So, how can we obtain this? So, there is something magical called as PF guarantee result, that Perron-Frobenius guarantee. Basically, what it says is that if A is irreducible, then firstly, the maximum eigenvalue is positive, and there exists a unique eigenvector whose all entries are strictly positive. We need this. We don't want any of the entries to be negative valued. So using this, like this result, we can guarantee to obtain such a vector C. Whatever, like out of that, we now calculate those importance, and maybe I think this deserves a much more detailed discussion. However, the book also doesn't mention much about this. There are some references, maybe we can deeper into those. But what it says then is like for negative non-negative weights, the same definition applies with local form. So it calculates the, I think it calculates like the matrix times the component vector. But not exactly clear how this captures the importance. There is something magical that is going on. Hmm. So it says this thing that if G is disconnected, A is reducible, and the global principal eigenvector concentrates on the components with largest spectral radius. So basically, if it has multiple components, it is like it will be like block structure, but the non-zero components will correspond to the each of the non-zero entries of the eigenvector will correspond to the components. But again, that is actually also connected with spectral clustering. Spectral clustering was, I think, it was taught when we were in our MStat. So there, this kind of things also arise, but not going too much into depth. I hope it is clear like what we do. Basically, this algorithm, we just compute the eigenvalue related to the adjacency matrix. And out of the entries of this eigenvector corresponding to lambda max, we calculate this centrality measure. So for this, yes, Pratik. I mean, you can ask, but I am not sure whether I can answer. Ah.
I doubt whether you will not be able to answer. You have answered so far. So
Hmm.
I hope there is no background noise coming from my end, right?
No. And from my end, is that clear?
No, no. There
Okay.
is a truck in front of my house and it's
Huh.
vibrating at a very audacious frequency, but Zoom's noise cancellation is very good.
Yeah.
Anyway, I wanted to understand
Hmm.
just one slide before this when the formula was given for that eigenvector based.
Hmm.
Yeah. So
Yeah.
here I got a little confused because this we are using C multiple times. So I just wanted to confirm that I'm getting it right. So
Yeah. Yeah.
C bold, C bold, which is bolded
Yes.
C,
Hmm.
that is the eigenvector, and
Hmm.
this the normal C is actually denoting the eigenvector centrality of vector V.
Of vertex V. Yeah. Yes.
Is it
So. Hmm.
then inside
Hmm.
that alpha summation, and inside the summation there is again the same C. So is it like a recursive formula?
Oh, actually, these are like, so basically the C vector, each of the entries are denoted with CV. So this C vector, it is like C bracket 1, C2. up to Cn, where n is the cardinality of your graph. You have n vertices.
Uh,
Okay. So there are n components in this vector because A is n cross n. Now, okay, I think I understand what's the confusion. I should have written this with a different subscript, C centrality, whereas this C is the entry of this vector. So thanks for pointing it out. This is a
uh,
wrong notation. Yeah, sorry for the confusion, but this is actually left hand side is the centrality, and right hand side you are just summing on the components of the eigenvectors bold C, which are neighbors of the vertex V. So
okay.
this
I
n of
I
V
got
is neighbor set.
I got that the C on the right side is basically an element
Uh-huh.
in the vector of C.
Yeah. Yes.
I want to
Yes.
understand that U must be the neighbor of V. Um,
Hmm.
but like eigenvector, here neighbor of V being V is
From the
how
graph.
V is in the graph. V is in the
Hmm.
graph.
Hmm.
So
So this is like
I
NV.
just, Hmm.
Basically, all you would take the summation over all such pairs UV which belong to the H set. So, like you.
intuitive why I'm having difficulty is
Hmm.
because
Hmm.
when we get an eigenvector, that is
Yeah.
not necessarily going to be the same column from the matrix. The eigenvector can be a column vector or a row vector which has completely different elements. So
Yes. Right. Hmm.
when I'm looking at this formula and inside the summation, there is this
Hmm.
condition that
Hmm.
U is a neighbor of uh, this U is a neighbor of B.
V. Yeah. Hmm.
Then this C of U, like what
On.
exactly is what exactly is it? Which
Oh.
position of the eigenvector is it denoting?
So basically, the thing is of the like the magical properties of this eigenvector is helping us. So you have a matrix whose
Hmm.
rows and columns are properly ordered as per the vertexes, and this ordering or the information is preserved inside the vector, because if you think about it, A C, so the ith row will be multiplied with C, the jth rows will be multiplied with C. So that ordering is preserved, and also the information about the importance will be same in the same order as the vertex. So each entry will correspond to the corresponding vertex of the eigenvector. So that ordering is preserved. So that's why it is helping us out.
Okay.
Like, so the thing is that if your graph has two sets, two disjoint sets, so basically what will happen? It, yes, Abradipta also has a question. Hmm. Abradipta, you raised your hand. You can ask. Okay, maybe there is some internet issue. So just continuing what Pratik asked. So yeah, and is that clear, Pratik? By the way?
Uh, yeah, I think for most of it you addressed it. I will have to rethink on it offline
Ah,
because I understand given the structure of the matrix itself, some things are helping other things out.
yes.
Yeah,
Yeah.
so Abradita
Uh-huh.
said in chat that whether she's audible or not, at least to me, you were
No,
not audible
not
the
me.
last.
Yeah, same here.
Audible now?
Yes, yes. Now audible, huh? Now
Yeah, I
audible.
have a question that like
Uh-huh.
C, the vector is itself eigenvector for A, right?
Yes, yes.
And A
Hmm.
has only one and zeros in a row, uh, like
Hmm.
corresponding to whether the age is there or not, like
Hmm.
the connection is there or not. So
Hmm.
I
Hmm. Hmm.
think like, is it not that CV is equal to alpha into that summation? Is it not
Hmm.
coming directly from the part that C is the vector C is equal to A into C itself, like alpha into A into C? Because like when I'm doing AC, then
Hmm.
that row will contain only ones at those places where there is a connection, like which belong to the
Yes,
neighborhood.
correct, correct. Yeah.
And then
Hmm.
that is how, on the left hand side at a particular place of C, I'm
Hmm.
getting alpha into summation of all those elements where
Hmm.
at that row we have one.
Yes, true,
So,
true.
like, is it how
Hmm.
we are getting that equation CV is equal to alpha into a summation CU directly from
Okay,
C is equal to
okay,
alpha
right.
into AC?
Okay, so you're saying that this is automatically coming. Huh, so that is correct. Okay, so what she's saying is that wherever you will be in the neighboring set of vertex V, we will have a 1 in the entry. And as a result, when you just multiply A times C, or yeah, C is equal to alpha A times C, that is satisfied. So there we will have automatically this equation satisfied, in the sense that the Vth entry will be the Vth entry of this matrix, and the Vth entry of this matrix is basically the, what is that is a element, and that is the multiplication of the Vth row with the vector C. Yes, I'm coming to Ishan's question, just 1 minute. So it is multiplication of the Vth row of A with C, and the Vth row will be either 0 and 1. Where will it be 1? Where this neighbors are there, like only those points who are neighbor with this V. So those points will come up. So this is like the solution or the simplified form of this equation only. So that is what yes, so that's a very good point. I didn't think about it, right? Yeah. So this is the solution. This is the solution. Yes, now Ishan has a question.
Yes, Pandanda.
Hmm.
As Abraditadi was saying, I believe
Hmm.
like the analysis involved in these type of equations is very much similar to how do whenever we deal with Markov chains,
Right.
especially similarly when we do the first step analysis, or I mean the limiting hitting time
Hmm.
formulation. So
Hmm.
similar to the ones and zeros placed whenever we are moving from one such vertex to its neighboring vertices, we follow the transition probabilities according to a particular row corresponding to the starting vertex. So
Yeah.
in that manner, I mean the equations come automatically in that
Hmm.
form, and moreover
Hmm.
all
Hmm.
such types of equations follow the essential law of, I mean, the harmonic equations, because
Okay.
wherein from
Oh,
one
I
such
didn't know about
vertex
that.
we are moving.
Hmm.
Yeah, I mean, harmonic equations in that sense, I mean, we could start from one vertex and then the directions wherever we're going based on
Huh.
the other
Hmm.
vertices which are adjacent to the initial vertex from where we are starting. And
Hmm.
then I mean, the equations, they resemble these harmonic principle in that sense.
Okay. Oh, okay. Okay. So the kind of a recursive dependence is there.
Yes.
Yes, that is there. Yes, it is connected with stochastic process. The only difference is that the entries are not summing up to 1. These are like binary.
Yes.
So wherever there is a non-zero
Binary.
probability, it is here 1. Right. Yeah. So for weighted matrices, that might be the case. For weighted matrices, it will be like that. So yeah, that's another good point. Thank you for raising that. Yes.
I would like to ask,
Yes.
I
Yeah,
am
I have a
thinking of,
question. Hmm.
yeah, sure.
Hmm.
Um, I'm I'm thinking of, I mean, I'm inclined
Hmm.
towards pursuing a research in the line of, I mean, random graphs and random matrices. So,
Okay.
as I was, as I'm going through the lectures that you're giving, so
Hmm.
I was wondering whether for aspirants like us, based in
Hmm.
the topics of such random graphs or random matrices, is
Hmm.
the like package like igraph or any other such packages, or so far, so as I'm seeing igraph, are these types of packages very helpful, especially when we want to back up any sort of theoretical explorations we're going through, followed by some simulation approaches like
Okay.
centrality or
Huh.
degree adjacency? So is this
Uh,
package helpful for theoretical probabilists as well?
Yes, because like there, whatever you are doing, say you want to do that in basic probability, there you would have used the basic functionalities in R, right? The basic
Yes.
packages in Python or whatever. That same thing in the theme of graph theory or random graphs is there in iGraph, and this SAND package, this SAND package that these authors have created. I think
Yes.
that will be quite useful for many of the analysis. It would be useful at least getting simulation results and also most of the intricate plots. It is quite useful. Yeah.
I see. Oh,
So I also have the codes, and last time I think last session we shared the code. I will also share the codes for this session for all the graphs that I have added here. Okay. That might
okay.
help you as well.
Thanks.
Welcome. Yeah. So I am continuing then. Thanks to all of like Pratik, Avradip, and Ehsan for their very valuable points. Now this aspect is much more clear to me. And this is like a paper by Cuts. The author's name is Cuts, and they have proposed this measure. And this is like just the solution, the eigenvector. So that is actually the same C. So now I am just taking my words back. So it is the same C. Basically, this is not a recurrence, but this is the solution that we are obtaining from this matrix equation, eigenequation. So this is how it would look like if you used this eigencentrality values to zoom in and zoom out, like the vertex sizes, to inflate the vertex sizes. Now, the the generalization of these notions of centrality for directed graphs has two defined ideas. These are hubs and authorities. So for directed graphs, AUV is 1 if there is an edge from U to V, and it is 0 otherwise, right? So if you think of AA transpose, so there, what will happen? A transpose will have like, so UV times VK, the summation over V. So that will imply an H from U to V and an H from V to K, right? So this is carrying information about source similarity. However, A transpose A will carry information of target similarity. So basically, the UVth entry of A transpose, it counts how often the source U and V co-point to the same target. Now, since we have taken a transpose here, so it will be like if you are taking the row and the column of A transpose, the column of A transpose is a row of A, right? So, like a little bit thought in that direction. So that matrix multiplication carries information about how often sources U and V co-point to the same target. So U pointing towards some K and V pointing towards that same K. We are counting how many such Ks are there, right? So that is a property of A transpose, and just the reverse of it is they are encrypted inside A transpose A. It counts how often targets U and V are co-pointed by the same source. So K points to U and K points to V, the number of such Ks. So this is a very nice idea. I mean, so simple the idea is, but still how much you can get actually out of that just by multiplying some matrices. So if you do the same analysis there, like if you calculate, I think now you're calculating the leading eigenvectors of A transpose and A transpose A. So these entries will be large for nodes that point to many strong authorities. So these are hubs codes, and the A transpose A will be large for nodes that are pointed by many strong hubs. So A transpose A, that same thing, right? Pointed to targets, how often targets U and V are pointed by the same source. Okay, so now by seeing this graph, it will be more clear. If you now see for the same graph, the vertex sizes are proportional to the hub and authority scores. If you see the hub scores, this is a directed graph, by the way. I should zoom in a little bit so that it is more clear. The hubs, the larger blobs, are like those who are pointing to many nodes. And here, the authorities are those who are pointed by many nodes. Okay? So I hope that is clear. Right? So this is obtained using the same trick of eigencentrality when applied on A transpose and A transpose A. And the most important thing is this is for directed graphs. This is for directed graphs. Okay, so we are now moving ahead. We have the next thing here as characterizing through edges. So now, till now we have characterized through vertices. We can also use edge to characterize in the sense that we can use something called as edge betweenness centrality, which measures the number of shortest paths between other vertices that are passing through a particular edge. Instead of just seeing whether it passes through a vertex, you can see whether it passes through some edges. The more it does, you will increase the weight. And that gives you a weighted graph where the edge width has been made proportional to this betweenness centrality for edge. This is how it looks like. Now, this is like the most strongly connected kind of edge because most of these edges will pass through this common edge. So it is like a bridge. Similarly, there are other strong edges or edges with high centrality. So this is another, just an extension of the idea applied on edges. Now we move on to the next section, that is cohesion. So the idea of cohesion is also very interesting. Now, the question is basically saying that how densely a network is connected as a whole, how densely it is connected. So how stuck together or tightly connected a group of vertices is the definition of cohesion. We can characterize cohesion at different scales from local patterns to entire network structure. Okay. Now we can also measure cohesion by identifying specific types of subgraphs. So that we will see. In fact, a clique is a subgraph that is often used for obtaining the values of cohesion. What is a clique? Clique is something that is very much studied in random graph theory, network theory, and probability also. So a clique is basically an edge, and a clique of order 3 is a triangle. So you can understand like it has say, k many vertices and a complete graph with k many vertices. Basically, that is a clique. So in any graph, any set of edge and vertices, you can count how many these cliques of different orders are there, right? Now, if say the values are quite high, say there are many 4 cliques inside a graph, that means there are many subgraphs which are cliques of order 4. So that is quite densely connected. But with increasing size of k, it is more computationally challenging and also less expected that you will have a complete clique, right? It is less expected. But however, you can have something which is very close to a clique, but not exactly a clique. Say we have 4 vertices, just one edge is missing from being a perfect 4th order clique. So there the concept of uh, k core like is there, cohesion is there. So what are k cores? Is basically you can think it as a maximal subgraph. So maximal subgraph is the largest possible subset or subgraph in which every vertex has degree at least k within the subgraph. So from a plot, it will be immediately clear what I am trying to say. So this is the same karate network data. And there are 4 colors here, which has been used, right? And the 4 colors correspond to 4 cores. So the 1 core nodes, like the node which has only 1 degree, you can see no edge here except this one has degree 1. So this is the only one with k core, I mean 1 core degree. So it is kind of in the outskirts of the network, very sparsely connected or in that way. But there are nodes like these ones which have at least degree 4. So these are like the 4 core nodes. You can actually increase the value of k. There are some 5 core nodes also, but this is a nested set, right? I hope that is clear why these are nested set. K cores are nested because a k plus 1 core is always contained within a k core. Like if you see these vertices, these few vertices have much higher degree than 4. So maybe if you say make a 6 core, you allow k to be as large as 6, then there will be a few more colors. Here I have increased the intensity with the number of cores. Now this is one way to visualize this. There is also a like eccentric view. It is like this. However, the connection or the edge structure is same. Just we are seeing it in a concentric circular manner. Each points with same value of k core, like k, say k is 4 is placed here, k is 3 is placed here, 2, 1. So lower k values are placed outside. So this is another important concept. And the next concept here in cohesion is about density and relative frequency. So what is the density? The density actually measures how crowded a network is with edges. So it is like the number of actual edges to the number of potential edges, maximum number of potential edges. So a density of 0 means there is no edge. All vertices are disjoint, not connected. Or however, a density of 1 means that the graph is a click. The graph is itself a click. So basically it's a complete graph. So all possible edges are actually present. So as a result, the natural definition for any subgraph H, the density of H is, in an undirected graph, the cardinality of the existing edge set of that subgraph H divided by the maximum possible cardinality. For undirected graph, it is VH choose 2. For directed, however, it is like n into n minus 1, right? Both ways it is allowed, 2 into n choose 2. So these are the definitions. And for the same character data, we have computed the this values of like density. And here, what you would see is that the overall network, so for our entire network, we can give one single value, right? That is the density score, that is 0.139. That means around 13% or 14% of all possible edges are present. But if you see the instructors group and admins group, individually they are more connected. The analogy of this can be given as in analysis of variance. You have two groups. In between the groups, if you make them as separate, basically the groups has lower variance. But if you combine them, the variance sort of increases. Just like here, the overall density decreases when you combine them. Okay, Pratik has a comment. From the outside, we are united, but from the inside, we are more divided. Yes, that is the case for many, many things in this world. So thanks for that deep comment. And here the interpretation is like on the same lines as Pratik mentioned, that the local neighbors around two leaders are significantly denser than a network as a whole. This confirms that these groups were highly cohesive, which helps explain why the club eventually split around them. Okay, so this is like kind of a causation that we are trying to give. We are trying to do some inference, some sort of inference, some conclusion. Like even if that splitting didn't happen, maybe we could predict that the split was about to happen, right? Because of this pattern inside the network. So this is the concept of density. Next comes a very related concept, that is clustering coefficient. Now the clustering coefficient, what does it measure? It measures the tendency for nodes to form tightly knit groups. So basically you can understand that the same concept of cluster basically Each cluster is tightly knit groups, but in between two clusters, there are very less connections. So it basically answers the question that are my friends also friends with each other? Where it is more true is more likely to be a cluster. So local clustering coefficient is calculated for a single node, and global means the average cluster value of the entire graph. But these are just some notions. A concrete definition is something called as transitivity. What is a transitivity? So it is a global network property. So for each network, you can give one value. So that is very closely related to clustering coefficient. What does it calculate? It calculates the ratio of closed triplets, that is triangle, to all possible triplets. Now by triplet, it means like it is like this, which means like it is a path of length 2. It can be open or closed. If it is open, that means say I am friend with someone, that someone is friend with someone else, but that someone else is not friend with me. That will be a open path, right? But if that is closed, that means we are mutually friends. So that is what we are seeing. We are actually counting all such connected triplets, not necessarily closed, but on the numerator, we are seeing number of triangles. Now there is a 3 that is multiplied here. That is interesting. Why the 3 is multiplied? It is required because otherwise we will undercount. If you just consider the number of triangles, then inside each triangle, you can have, say, how many? You can have 3 possible triplets that are open, right? So this ratio is now valid. It is properly normalized, and this will give us the idea of the like the clustering, the global view of clustering, how much the points or the vertices are neat to each other. Okay. By the way, this is already 6. So just confirming, should I continue or should I stop?
So this is 4.3 going on, right?
Yes,
Is
4
it
point.
about to end or is it going
Yeah,
on?
actually, the last few slides very much related. So maybe we can wrap that thing up. Maybe I can end it in 10 minutes. Is that okay then?
Yeah, it's fine with me.
Okay, okay, thank you. So this is the concept of transitivity. Some slides are like this, just one result, one outcome. And here, for example, we have for this karate club, the transitivity value is 0.255, which means roughly 25.6% of the open paths of length 2 are closed. This is a moderate level of clustering. So similarly, there is another notion of reciprocity that is, however, for directed networks, directed graphs. So what does it do? It measures the likelihood that connections in a directed network are mutual. That means if I link to you, do you link back to me? So how many proportions or the proportion of edges that are reciprocated in the sense that if it is 1, it means every connection is a two-way street. The network is essentially undirected. So all connections are two-way. So perfect both-way connection is there. A reciprocity of 0 means that these are not mutual connections. The transactions are one way mostly. Like for the AIDS block network, that data was also discussed in the first session. The reciprocity is very low. So only about 3% of the links in AIDS block network are mutual. So it confirms that this is a network with a largely one-way flow of information. This is the case with many websites in the like www, the Internet of Things, IoT. Many websites are like the hubs, right? So many small websites are pointing towards them. And those big websites, they have millions of connections, millions of nodes which end up there. So very low reciprocity in that case then. Next here we have the notion of connected components. So a fundamental question is, in a network, basically, is the network a single piece or it is broken into separate parts? Here I have written separate islands. So a graph is connected if you can get from any vertex to any other vertex. And if not, basically it means it has many disjoint components which are connected in between. So in many real networks, one component is vastly larger than all others. This is called the giant component. Like if you think about same websites, there are a few websites which are very, I mean, there are a few components which are very huge and some very disjoint components. Like this whole concept of deep web. These are a few in the Internet of Things. These are a few websites which are like very difficult to access and mostly disconnected with the ordinary or the surface web, right? That is easily accessible or ordinarily accessible through Chrome and other normal browsers. So, yeah. For the East protein network, if you see the components, so there are 63 components of size 2, 13 of 3, and there is one huge component having almost 2000 many proteins. So this is actually like a very big subgraph or a subnetwork which is doing most of the functionalities. The rest are all special interactions that are going on. These also have importance, but this is like the most active component. Okay. So this is what it says about the East protein network, and this is often the case with many real life data, and similar kind of models are also there to model a similar situation. So what is next? Next we have cuts and flows. What is cuts and flow? So these are like some small sections. So I have just covered 1 and 2 slides. Basically, here we measure network's robustness by identifying its critical points of failure. That means if you just cut one edge, the graphs will become disconnected. So vertex cut is a set of vertices whose removal would disconnect the network. A single vertex that can do this is called a cut vertex or an articulation point. These nodes are critical bridges holding the network together. So that's, I hope that's very clear. And so in East networks data, its vertex connectivity is 1. That means if you just remove one single edge or say one vertex, yeah, so one vertex, you just remove one vertex which is connecting the whole thing, so it is enough to fracture the network. It will break into smaller and smaller pieces. So in fact, there are 350 such articulation points. So that's very interesting. That means there are many bridging proteins which are very important for the functionality of the yeast bacteria. And there are 350 such articulation points. So that is there. And for directed graphs, connectedness has two meanings. One is the notion of weak connectivity and strong connectivity. In weak connectivity, the graph is in one piece. If you ignore the direction of the edges, there is a path between any two, but not necessarily directed. So basically, there are connections, but most are one way. But strongly connected means there are connections and both are mutual. Like this import export business, that is say one country is exporting most of its goods to other countries but not importing that much, so then that is weakly connected. Similarly the other way, and the comment is also here for AIDS block network, it is weakly connected, not strongly. Okay, so now we are almost nearing the end. Here we have the graph partitioning. Okay, I think maybe we can cover this in the next session, because this whole idea of community detection is important. Uh, Maybe with that we can wrap up this chapter. Otherwise, I can drag it, but it will be unnecessarily long. And not, I mean that also too much for me also. So is that okay if we do this in the next session? Start with community detection nicely, properly.
Yes, I mean, if it's important, then we
Yeah.
can do it in start from a new session.
Okay. Pratik is saying full reciprocity. Okay. Yeah, same from my side. So strong connected decision. Okay then. So I think we can end the session here. So thank you all. And I wish through this recording a very happy puja. Today is Mahalaya, so Shubha Mahalaya to everyone. So maybe we will have our sessions after puja. Most of us will be outstation during and after puja. So okay, thank you. See you all soon.